Oh, okay, let's get things started. All right, today's the 25th. So answer to your names, please. BN, not here. Bilik is here. Kane, did I see Kane? Nope. Camacho, Kramer, nope. Carol Paczynski, that's you. Joshua Lopez is here. Brendan Lopez, I don't see that person.
I'm here on the Zoom.
Malberg is here. Martin, I don't see Martin. Reed, I don't see Reed.
Martin's here.
Ritzlaff,
Bianca Reed is here.
Richie, I don't see Richie. And Yako Shenko is here. All right. Yes, this part working.
Sir, can you unmute yourself?
Okay. Now we're in business. All right. So now I should be able to share my screen. Okay. All right, so let's talk about balancing equations. Now, firstly, let's talk about equations, right? Chemical equations. These are used to basically summarize what is happening in a chemical reaction, right? And there are a couple of parts that you will see in any chemical equation that you'll see in any chemistry textbook or any chemical literature, right? Usually, you'll have the reactants on the left side. So reactants will be on the left side of the equation. Then you have your arrow, and then you have your products, which are the substances that are produced, right? And typically we use formulas, and we're going to go look at a couple of examples. So you use the formulas to represent the reactants and products, and sometimes you see some information here above or below the arrow, which tells something about the reaction condition, right? So for example, you might see heat, right? Which means that you have to heat the reactants in order to get the products. Or you might see a specific temperature. You might see something like 200 degrees, which tells you the temperature, the actual temperature of the reaction, or the temperature required to make the reaction go. Also, when it comes to the formulas of reactants and products, you might see some what we call state symbols. So let me give an example. Let's say we have hydrogen peroxide, right, which is in an aqueous solution, to form H2O, which is a liquid, plus oxygen, right? So, which is a gas. So the G, L, and the AQ basically tells you about the state of the substances involved, right? AQ means aqueous, G means gas, L means liquid, and there's another one, S means solid, right? So you might see that also in a chemical equation, which gives you more information about the conditions of the reactants and the products. Another thing I want to mention too, and this has to do with the conservation of mass law, right? If you remember, the conservation of mass law says that in a chemical or physical change, matter is not created nor destroyed. In other words, whatever the total mass of the reactants, let's say you're dealing with a chemical reaction, whatever the total mass of the reactants you start off with, the mass of the products will be the same, all right? So that is basically the conservation of mass law. Now, the reason why that is because if you look at things at the microscopic level, atoms are not created nor destroyed, right? In other words, the number of atoms of each element on either side of the equation will be the same. And this is what balancing equations is all about. It's about representing that fact. The fact that the total number of atoms of each element in the product or in the reactants that you start off with will be the same as those same atoms in the product, all right? So I'm going to use this example that I have here already to demonstrate that. Now, if you look at this equation carefully, right, you'll see that you have two hydrogens here, right, because of this subscript here, and you have two hydrogens there, which is okay, which is fine, which is what you'd expect, right? You'd expect that the number of hydrogen atoms to be the same on both sides. However, if you see here for the oxygen on the left side, you have a total of two oxygens here, right? But on the right side, you have one oxygen here, and you have two here. So obviously, there is no balance. The number of oxygens are not the same on both sides. So balancing equations is basically what you would do in a situation like this, where the atoms of a particular element are different. The number of atoms of a particular element are different on both sides, right? So the question now becomes, how do we go about balancing the equation? Well, let me tell you what you cannot do, right? What you cannot do is basically change the subscripts, right? So in other words, you might be tempted, for example, to remove this 2 here and replace it with a 1, right? That is incorrect. You cannot change any subscripts in an effort to balance the equation, right? So let me put back the 2 here. Right, so you cannot change any subscripts. Another thing that you cannot change is, or what you cannot do actually, is simply add an atom to one side or the other. So you might be tempted to just add an oxygen here to balance the oxygens on both sides. Again, that is incorrect. Cannot do that, right? In fact, the only thing you can do in an effort to balance any equation is to change the coefficients. And the coefficients, and I probably should have told you this earlier, the coefficients are basically the numbers that will be placed in front of the formulas for the different substances, all right? So the only change you can make would be changes to the coefficients, all right? So in this particular case, you might be asking, okay, so how can I make sure that the oxygens are equal in order to change, in order to balance it, right? And what I would do in this particular case is that I would put a coefficient of a half here, right? Now you might be wondering, why would I put a half here, right? Well, remember you have 2 oxygens on this side, right? And remember you have 1 oxygen here, right? So half of 2 gives you 1, 1, right? And 1 plus 1 gives you 2. So now the oxygens are balanced, all right? The hydrogens are already balanced, and now we have successfully balanced the oxygens. However, this will not be the final answer, because what you have to ensure traditionally is that all the coefficients are integers, whole numbers, right? So how do we convert this half into an integer? We simply have to multiply everything, all the coefficients in this equation here, by 2. So if you multiply the entire equation by 2, you're going to end up with 2H2O2 to give 2H2O plus O2, right? And that would be the final answer. And what I recommend students doing when they're doing this for the first time especially, is that they check to make sure that everything is balanced, which it is, because you have 4 hydrogens here on the left side of the equation, you have 4 hydrogens here on the right side, and then you have 2 times 2, 4 oxygens on the left side, and here you have 2 plus 2, 4 oxygens on the right side, and therefore everything is balanced, all right? So that's basically how you go about balancing an equation. Again, let me stress that this is a most important and fundamental skill that you need to balance, or you need to master, I should say, because pretty much a lot of what we're going to do later on will be based on what we're learning now, all right? Okay, any questions about this? Any questions? Any questions? Any questions? Any questions out there in Zoom? Any questions? Okay, so, let me clear this. And I'm just going to go through a couple of examples. Starting with N2 plus H2 to give NH3. All right, so based on what we have just discussed, how would you go about balancing this particular equation? Remember, the only changes you can make are changes to the coefficients, which are the numbers that you place in front of the different formulas. All right, so how would you go about balancing this equation? Out there in Zoom, please feel free to chip in if you have the answer or if you think you know what the answer is.
You would put a 2 in front of the NH3 and a 3 in front of hydrogen.
Very good. That's what I would do too. Now, the reason why she said they put two, by the way, who said that? I'd like to give credit to. Person to contribute. Okay, so who was that who just spoke a while ago?
Stephanie.
Stephanie King, okay, thank you very much. So the reason why Stephanie, said that you should put a two here is because you have a two here, right? So to balance the nitrogens, we put a two here. Now, by putting a two here, we have also doubled the number of hydrogens on the right side. So that means that we have a total of 6 hydrogens on the right side. And therefore, that means we need to put a 3 here to make that 6 hydrogens, right? So therefore, that's it. The nitrogens are balanced and the hydrogens are balanced on both sides. So therefore, this will be the final answer. Okay. Any question about this example? Any questions? Any questions? Any questions? Okay, let's step up the level of difficulty a bit. Suppose you're given HNO3 form NO2 plus H2O plus O2. Okay, so let me hear what ideas you guys have about this particular unbalanced equation. How would you go about balancing this equation here? Now, let's start with the hydrogens. How many hydrogen atoms do we have on the left side? One hydrogen, right? How many do we have total on the right side? 2. So how would you go about balancing the hydrogens? If you have 1 on this side, you have 2 on this side, how will you balance the hydrogens? With a 2 in front of the nitric acid, HNO3, right? Okay, now what about the nitrogens? Because of this 2 here, we have double the nitrogen on this side, we have only 1 here. So what do we do? To balance the nitrogen. The 2 here, exactly. So the only other element left is the oxygens. So how many oxygens do we have total on the left side?
4.
4, you sure? This is the 3 right here.
Oh.
On the left side.
Oh, sorry, I thought that was a 2.
Oh, okay, let me make sure that is.
Oh, 6 then.
Okay, so we have a total of 6 oxygens on the left. How many oxygens do we have on the right? We have 4 plus 1, that's 5, plus 2, that's 7, right? So we have 6 oxygens on the left side. We have 7 oxygens on the right side. So how would you balance the oxygens in this case? How would you make sure that the number of oxygens on both sides are the same? Anybody? How about you guys out there in Zoom? Any ideas? We have 6 oxygens on the left, and we have a total of 7 on the right.
double the number of oxygens on the left.
So you're saying that that should be 4? I'm saying, what am I saying? Yeah, that should be 4, yeah. You double it, right? But what about the rest of the equation? If you double the number of oxygens, you're gonna double also the number of hydrogen, right? So if you increase that to 4, that means what do you need to put here?
A 2.
Okay, and you also need to change this because this 4 here will increase the number of nitrogens from 2 to 4. So what do we need to do here?
Change it to a 4.
Exactly. All right, so the final answer is going to be 4HNO3 to give 4NO2 plus 2H2O plus O2. Now let me just show you another way of doing it. This is the way I would prefer to do it. I'm going to go back to where we had 2HNO3 plus, I'm sorry, not plus, around then 4NO2 plus, let me erase this here. H2O plus O2. And we had a 2 here, all right? Okay, what I would do, in order to balance the oxygens, I would put a coefficient of a half right here, right? Because by putting the half here, that means that this becomes 1 oxygen plus 2 plus 1, 2 plus 4, which is 6, which balances with the 6 here. And then I would multiply everything by 2, and I would get this as a final answer, right? So that's another alternative way, which is the way I prefer, to be perfectly honest. But of course, this is not the only way of doing it. But you will get the same answer if you do it this way, all right? Okay, any questions about this example? Any questions? Any questions? Any questions?
Can I ask a different question?
What do
Still
you mean?
about this though.
What about it?
On the PowerPoint, it said to come up with the reaction for combustion and stuff like that. Do
Oh,
I have
okay.
to know how to do that?
We're gonna get to that, don't worry. In fact, we're going to get to that in the next chapter. I'm going to discuss the next chapter as well. Because we're going to talk about different types of reactions, and combustion is one of those reactions we're going to talk about. Okay, any other questions before we move on? Any other questions? Any other questions? All right, are you finished writing this down? All right, so let me get rid of this here. And let's do another one, which is a bit more challenging. Okay, where is this thing? Okay, suppose you're given suppose you're given C5H12 plus O2 to give CO2 plus H2O. All right. Okay, so let me hear what you guys think about this one. How would you go about balancing this one? Let's start with the carbons on both sides. How many carbons do we observe on the left side? 5, right? How many carbons do we observe on the right side? 1, right? Okay, so how would you balance the carbons? You have 5 on the left, 1 on the right. So what would you do?
Right.
Put a 5 in front of the carbon on the right. Very good. Okay, what about the hydrogens? We have 12 hydrogens on the left. We have 2 on the right. So how would you balance the hydrogens in this case? Again, you guys out there in Zoom, please feel free to contribute. We have 12 hydrogens here. We have 2 on the right. So how would you balance the hydrogens in this case?
We would put a 6 in front of the H.
6 in front of the H2O, very good. So now, the only other element left is oxygen. So based on what we have here, we have 2 oxygens on the left, and over here we have 10 plus 6, 16 oxygens. So how would you balance the oxygens in this case? We have 2 on the left, 16 on the right. Okay? Yeah, correct. And that's it. Everything is now balanced. You have 5 carbons on both sides, you have 12 hydrogens on both sides, and you have 16 oxygens on both sides. So now the equation is balanced. All right? Okay, very good. All right, I'm going to again step up the level of difficulty a bit. Suppose you're given suppose you're given that. How would you balance it?
I would start with sodium and put a 3 in front of NaOH.
Okay, very good. The 3 in front of the sodium hydroxide. Anything else?
Put a 3 in front of H2O.
3 in front of H2O. And I think that's it. Don't think there's anything else you need to do. But again, just to quickly check through, 3 sodiums, 3 oxygens plus 4, 7 oxygens, 4 plus 3 oxygen, 7. Okay, so that's balanced. 3 plus 3, 6 hydrogens, 3 to 6 hydrogens. And we have 1 phosphorus here, 1 phosphorus. So yes, the equation is balanced, right? Okay, any questions about this one? Any questions? Any questions? All right, let's make it a bit more difficult. Suppose you're given. Suppose you're given, okay, let me try this one. AlOH3 plus H2SO4 to give Al2SO4 3 plus H2O. All right, let's see if we can do this one without my help. Okay, so. What have you come up with? Anybody? Let's look at the aluminum first. How many aluminum atoms do we have on the left side? One, right? How many do we have on the right side? Two. So how would you go about balancing the aluminum? The two in front of here, right? Okay, very good. What about the oxygens? We have a total of 2 times 3, 6 oxygens plus 4, 10. And then we have 3 4s 12 plus 1, 13. Typically, let me just say this. Typically, if you have the same element distributed between two substances on the left or right side, we tend to balance them the last. All right? So let's move on to the sulfur because we have hydrogen between these two. So let's focus on the sulfur for the time being. And see how we take care of that. We have 1 sulfur here, and we have 3 sulfurs here. So I'll put a 3 here. All right? Excuse me. So now that we've balanced the aluminum and the sulfur, we can concentrate on the oxygens and hydrogens. Here we have 2 times 3, 6, plus 4, 3 times 4, 12, so that's 6 plus 12, that's 18 oxygens on this side. And here we have 12 oxygens here, right? So how would you balance oxygens? Because we have 1 here. If we have 12 here, what would you put here? To balance oxygens. We have 12 here. We have 18 total on this side, and we have 1 here. Ideas? Anybody out there in Zoom can answer that question? What do we put here for to balance the oxygens? Give me a hint.
It would be 6.
Exactly. Right, because when you multiply by 6, you end up with 6 plus 12 oxygens equal to 18, which is equal to the 18 on this side. So the only thing that we haven't looked at yet is the hydrogens in terms of balancing. Let me just erase some of this here. So as far as the hydrogens is concerned, we have a total of 6 hydrogens plus 6 hydrogens. And we have a total, so that will be equal to 12 hydrogens. And then on this side, we have 6 times 2, 12 hydrogens. So the hydrogens are already balanced. So this would be the final answer that you're looking at here. All right, so this would be the final balanced equation. Right? Okay, so with that said, I want you guys to start with assignment number 6. So I'm just going to hand out these to my students here who are in person in class. And for those of you out there in Zoom, I am going to publish that very same assignment. Okay, so assignment 6 is now published. Now I want you guys, because it's a pretty long assignment, but I want you guys to focus on section A. Let me download it here. Okay, so I want you guys to focus on section A, which is the first 2 pages, and then section B. And I want you to do up to question number, for now, we're just going to focus on question number 10 up to that point, right? So I want you to do that now. And because I want to also discuss the next chapter, which is chapter 7, which deals with the different types of reaction, right? So for now, that's where you're going to stop. You're going to stop at question number 10 on in section B. And of course, if you have any questions, feel free to ask. I think I'll give you guys about what's 11:36. I'll give you guys until about 11:50. Again here. Kane is here. Macho here. Kramer up here. Brendan Lopez is here. Ashton Martin is here. Retzlaff is here. And Richie. I don't see Richie. Okay. That's it so far. Where are you at so far in assignment 6? Good.
Start section.
Oh, okay. All right, tell you what, because I want to talk about the different types of reactions. So let me just get started on that and then we can call it a day. So, different types of reactions. If you watch a video concerning that, you'll learn that there are basically 5 types. Remember the order I placed them in. So I'm just going to go according to my memory. So the first type I'm going to mention is the. Okay, where it is, I just had it here. Hello. I just had my pen here. Ah, oh, goodness. Okay, so first type of reaction I'm going to start off with is decomposition. And basically, in the case of decomposition reactions, you have a compound, I'm just going to call it AB, and it forms 2 or more products. All right? And in most of these reactions, you'd have to heat the original compound. Oh, by the way, I didn't mention this. This triangle here is another symbol for heating, right? So whenever you see that, you have to understand that's what it means, right? So basically, in most of these decomposition reactions, you have to heat your original reactant in order to get your products. And a good example of this would be the heating of calcium carbonate. Heat it, you're going to end up with calcium oxide plus carbon dioxide, right? So in a decomposition reaction, you're starting off with 1 reactant, and you're going to end up with more than 1 product, right? That's decomposition. Now, the opposite of that would be what we call combination. So combination reaction is where we have A reacting with B, and they come together to form 1 product, A, B, right? Okay, what would be a good example? A good example of this would be Cl2 plus PCl3, I'm sorry, to give PCl5, right? So as you can see, you're adding 2 substances, they react with each other, and you end up with only 1 product, right? So that's basically what combination is, right? And then the third type we're going to look at is single displacement. In some textbooks, they call it single replacement, same thing. So I'm just going to put replacement in parentheses, it means the same thing. And basically, this is what happens in a single displacement reaction, right? Basically, this is what happens. So we have A reacting with this compound BC, and what happens is that A takes the place of B, so therefore A ends up being combined with C, and B is being displaced or replaced, all right? So that's basically what we mean by a single replacement reaction. A good example of this would be the reaction between sodium and hydrochloric acid to form sodium chloride and hydrogen. And to balance this, we're going to need a 2 here, a 2 here, and a 2 here, right? So that is a single displacement reaction because the sodium here is displacing the hydrogen from that compound. The sodium ends up being combined with the chloride, and the hydrogen is displaced from it, all right? So that's what we call a single displacement reaction, where one atom or group of atoms displaces another group of atoms or one atom. Let me give another example of this. In this case, we'll be using sodium iodide plus chlorine to form sodium chloride plus iodine. Right? And again, we have to balance this, so the two here, the two here. So in this particular case, this is another example of a single displacement reaction because as you can see here, the chlorine is displacing the iodine. So the chlorine or chloride ends up being combined with the sodium and the iodine is displaced, right? So those are just two examples of single displacement reactions, right? Some more things I need to say about single displacement reaction. In some cases, we can make predictions as to whether or not a single displacement reaction will occur. Because of course, by writing down an equation, that doesn't necessarily mean that a reaction will occur because you can write the equation down. And there is a series of elements placed in a particular order known as the activity series. Let me see here if I can bring that up here. And let's see here. Okay, so the activity series is basically a list of elements from the most reactive to the least reactive, right? And it's mostly metals we're dealing with here, all right? Basically, we can use this series to make predictions as to whether or not a particular single displacement reaction would occur, right? So I'm just going to make up an example just to illustrate what I'm talking about here. So let's say I write this down. Nickel plus MgCl2 to form nickel Cl2 plus Mg. All right. So let's say I give you that equation and I ask you, based on the activity series, I ask you, will that reaction occur? Right? Well, the answer is based on the fact that according to the series, the element that is higher will displace the one that's lower from its compound, right? So what I would do in this case is look for where nickel is in the series, which is right here, and look for magnesium, which is right here, right? As you can see, obviously, nickel is lower than magnesium. So if nickel is lower than magnesium, what that means is that this reaction will not occur. Nickel will not displace magnesium from its compounds, and in this case from magnesium chloride, right? So therefore the answer is that this reaction will not occur, right? On the other hand, let's say I gave you aluminum plus PbCl2 to form aluminum chloride plus Pb. And to balance this, we need a 3 here, we need a 2 here, we need a 2 here, and we need a 3 here, okay? So let's say I gave you that. And again, the question is, will this reaction take place? Well, I will look for aluminum. Where's aluminum? Okay, aluminum is here, right? Where is lead? Where's lead? Lead is here, right? So aluminum is higher in the series compared to lead. So what that means is that, yes, in this case, this reaction will take place, right? The lead, the aluminum will displace the lead to form the aluminum chloride, and lead will be formed as well, right? So basically, the key thing you need to remember when using this series is that the most active elements are to the top or above, right? And their reactivity decreases as you go down. So basically, the more reactive elements will displace the less reactive elements where there's a reaction where that can all right? Okay, any questions about this? Any questions? Okay, another thing I want to talk about, and this has to do with a different type of activity series, and that has to do with the halogens. Let me clear this here. So let me go back to Word. Let me delete all this here. Okay, now in the case of halogens, which are the elements in group 7, it starts with fluorine at the top, then chlorine, then bromine, and then iodine, right? And we don't usually look at astatine because it's radioactive, so we don't involve that particular element. Now, when it comes to these elements, what you'll find is that as you go from bottom to top, reactivity increases for these elements, right? So what that means is that the element above will displace the one below. Right? Okay, so in the case of, let's say, you're reacting fluorine with potassium chloride, right? To form KF plus Cl2. And to balance this, we need a 2 here and a 2 here, all right? So basically, we can predict, based on the series, that this reaction will take place. Why? Because fluorine is above chlorine. So that means that fluorine will displace chlorine from its compounds, right? Now, an example of a reaction that will not work is this one right here. Iodine plus KCl to form potassium iodide and Cl2, all right? And we balance it by putting those 2's there. This reaction will not work. Why? Because iodine is below chlorine. So therefore, iodine will not displace chlorine from its compound, right? So that's just a shorter activity series dealing with halogens, all right? So you need to remember these because you could be given an equation and you're asked to make a prediction as to whether the reaction will occur, right? So basically in both cases, the one that is higher in the series will displace the one that is lower. Okay, now, oh shoot. Okay, now we have dealt with single displacement, combination, and decomposition. Then we have a fourth category of reactions known as double displacement reactions. Right? Let me give you an example of that. Well, let me give a hypothetical example first. So let's say you have AB reacting with CD. Then what will happen? And this takes place usually with ionic compounds. What will happen is that there's going to be an exchange in partners. That A will displace C and come back with D, and C will displace A and come back with B. So therefore, you're going to end up with CB plus AB. All right? So there's a switching of ions that will take place in this type of reaction. So let me give you an example of this. If you take silver nitrate, which is an aqueous solution, and you add it to a solution containing sodium chloride aqueous, there will be a switching of partners. So the sodium is going to displace this, the silver is going to displace the sodium to form silver chloride. And the sodium is going to displace the silver to form silver nitrate. All right? And the thing about this reaction is that if you were to do it, let's say you did it in a test tube. You have your test tube, you have the silver nitrate, and then you have the sodium chloride. You're going to see the spontaneous formation of a white precipitate. And that white precipitate will be the silver chloride, right? This is a white precipitate, right? So let me tell you what a precipitate is, since I introduced that term. A precipitate is a solid that is formed, that is formed when two solutions are added to each other, right? So basically, oh, I made a mistake here. This should be aqueous, right here, right? So basically, you're mixing two solutions, two clear solutions, and upon mixing, you see, all of a sudden, you see the solid being formed, right? So we call that a precipitation reaction, and the solid that is formed is called a precipitate. So a lot of precipitation reactions result from a double displacement occurring, right? Okay, so that's double displacement. Let me give you another example. If you mix together lead nitrate 2 plus potassium chloride, no, potassium iodide, that's what it is. Aqueous, so these are two aqueous solutions. Again, you're going to have the exchange, right? So the lead is going to displace the potassium is going to displace the lead. So you're going to end up with KNO3, and this will remain in an aqueous solution. And you're going to have PbI2, which is going to be a solid. And in fact, if I remember correctly, this would be a yellow solid. So again, this is another example of a precipitation reaction. Let me make sure I balance this equation. You're gonna have a 2 here and a 2 here, right? In fact, let me see if I can locate a video of this. I think I remember seeing a video some time ago. So potassium iodide and lead nitrate reaction. Okay, so here it is. Okay, let me just let it run. It's important, more important that you see it. So I don't know which one is which, but this looks like, okay, so that's the lead nitrate solution. Okay. Right, now you see, upon addition of the potassium iodide, right, you get the spontaneous formation of your lead iodide, that's a solid, right? So we call that again, as another example of a precipitation reaction. All right, so that's a simple example right there. Let me go back to this here. So that's precipitation reaction. Okay, the final type of reaction I want us to look at is what we call the combustion. Okay, it's here. And this is used most often when it comes to organic compounds. So just to let you know, organic compounds are compounds that contain carbon. So organic compounds are compounds of carbon. With a few exceptions, but for the most part, this is true. Carbon, right? Now, most organic compounds either have a combination of carbon and hydrogen by itself. We call these compounds hydrocarbons, right? And then you have some other organic compounds which contain carbon, hydrogen, and oxygen, right? And then you can have some which contains other elements like nitrogen, sulfur, phosphorus, and so on, right? I won't go into all of that. I just want to focus on these two types. Now, the type of reaction that we'll be looking at here is what we call combustion reaction. Let me squeeze it up here. Combustion reaction is the type of reaction. And basically, whenever you see that term in chemistry, combustion, it's basically a fancy term for burning, right? So you have to put a flame to the substance and it burns, right? What happens when you burn anything in the atmosphere is that they will react with the oxygen from the atmosphere, all right? And in the case of hydrocarbons or compounds containing carbons, hydrogen, and oxygens, whenever you burn them completely, you're going to end up with two products. One of them will be carbon dioxide, and the other will be water, right? So even if you don't know what the formulas are for these compounds, you can predict what the products will be. The products upon combustion is always going to be carbon dioxide and water, right? So if I gave you any organic compound like C2H4, right? And I ask you to write down the equation for the combustion of C2H4. All you have to do is add your oxygen on the left side, draw your arrow, and then put the products, CO2 plus H2O. And then the only thing you have to concern yourself with after that is balancing it. So to balance this, you're going to need a 2 here, and you're going to need a 2 here, and then 2, 4, 6, 2, 4 is 2, 2, 4 plus 2, 6. You're going to need a 3 here. And this will be the answer, right? So that's basically what you need to do in order to balance a combustion reaction. If you know what the organic compounds is, all you have to do is start with the organic compound plus oxygen on the left side of the equation, draw your arrow, and then put carbon dioxide and water on the right side. And that's basically it, right? As far as combustion reactions are concerned. Okay, so with that said, that is it. Oh, almost there. All right, so I'm going to stop here for today, but I want you to complete assignment 6 and assignment 7, which I don't think I have published yet. So let me hold on. Okay, that's happening here. Let me go to files. So assignment number 7, where is it? 7. Oh, here it is. Why is that up here? So assignment number 7 is now published, right? Basically, assignment number 7 deals with what I just discussed, right? The different types of reactions. It will also involve some balancing of equations, so you get some more practice as far as that is concerned. And that's pretty much it. All right, yes, sir.
When will it be due?
Good question. Let me go to assignments. All right, so let me go here, edit assignment number 6. All right, so today is the 25th, right?
Yeah.
I'm going to let it be due by I would say by Friday. So let me do this here. It's going to be by Friday at midnight, and I'm going to do the same thing for let's see, is it I just forgot to publish. I'm going to do the same thing for assignment 7. Oh, and by the way, next week there will be no classes. So because of the professional development day that is for faculty members, so there will be no classes next week. So
Like all week or just Tuesday?
I mean next Tuesday, yeah. I'm sorry, I said next week. Next Tuesday. Mhm.
When is our next exam? What chapter, like specifically, is it?
Okay, so what were we tested on?
Or tested 1 through 3.
Yeah, let me see here. Okay, so the last test was 1 through 3. So let's see. Mm, I'm gonna make it be based on chapters 4, 5, and 6. Right? I'll let you know the exact date of the test. Because I think the syllabus says that the test will be next week, but I think I have to put that out. Right? But rest assured, I have to put it out because I would need to grade at least test assignment number 6. I'm in the middle of grading assignment number 5 right now, which I should have ready for you by the end of this week. So test number 2 will cover chapters 4, 5, and 6. Right? Okay, if there are no more questions, well, there can't be no more questions because there's no more time. All right, so that's it. So I'll see you guys week after next. And for those of you out there in Zoom, I will be signing off. Two. Two.